In this video, I wanted to show you how I selected and tested components for my backup power station build. I wanted this to be a 24-volt system, and I also wanted to charge it by using both solar and AC power. So the main components are solar panels, charge controller, battery, inverter, and battery charger. All those should be 24-volt compatible. Then we need other components such as wires, a main switch, fuse, circuit breaker or circuit breakers, and a box to keep all this inside so that I can make it portable. So the battery I selected was this one. This battery does not have Bluetooth, and I did not want Bluetooth in the battery. This is me unpacking the battery and checking the components inside the box. There is a product user manual. This manual contains very useful information such as parameters you need to program the charger for the battery. I should say the packing is very good. There's very little chance the battery could get damaged during shipping and handling in this package. The battery has handles which are very useful to carry the battery around. The initial voltage of the battery was 25.7. Next component is the battery charger. This is a 24-volt charger of 20 amp capacity. I'm just checking the components that came with the charger. This seems to be a very good charger. It has an aluminum housing which is good for cooling. The battery comes with Anderson connectors on either side from the battery to the charger. Initial testing showed it does actually charge at 20 amps continuously. Next piece is the solar charge controller. This is a 75 volt 15 amp maximum Bluetooth enabled charge controller. I chose this because of the small size, and also once it is inside the box I can monitor this using the cell phone app. It does come with a user manual which contains some useful information. It has the usual 6 connection ports, 2 PV ports, 2 battery ports, and 2 load ports. Temporarily connected this charge controller to the battery to test the Bluetooth function and the app. It was not difficult. As soon as it was connected, it started downloading firmware and updating the charge controller with the latest version of the firmware. Once the update was completed, the app started working normal. In the app, I had to select the battery type, and then once you select lithium iron phosphate battery type, you have to adjust the voltages by referring to the user manual of the battery. Here I am setting the absorption voltage and float voltage as indicated in the battery's user manual in the charge controller app. Once it is set, the charge controller would remember it, so you don't have to go back and enter these values again. Next item, solar panels. I purchased these 100 watt solar panels, 2 of them, so that combined it would be 200 watts. These panels are portable and they are folded into smaller packages by dividing the whole panel into 4 sections. You can open them up like this. And this panel is a bit heavier than what you normally think it would be by looking at it. On the back side, there's this pouch which contains a connecting cable and the output with MC4 connectors. These connectors are good for a variety of different devices. Here I am testing the solar panels by temporarily connecting them to the charge controller, and the charge controller is connected to the battery. For these to work, I had to connect the two solar panels in series. When you connect them in parallel, they won't work. Voltage is insufficient. To overcome this issue, I ended up purchasing this 200 watt solar panel, and the voltage of that solar panel, which is 40 volts, is sufficient for this system to work. The next main component is the inverter. This is a 1200 watt 24 volt inverter. I will show you briefly the unpacking and what is inside the package. This is a pure sine wave inverter, and it is suitable for travel. It claims to have less than 3% total harmonic distortion in the output. As usual, this inverter comes with the user manual and some vibration reduction rubber pads for mounting the inverter. Also, there was another document which outlined the ideal size of the battery that should be used with inverters of specified wattage ratings. The inverter came with some cables, a ground cable, remote switch, and two power cables, red for positive and black for negative. I thought these power cables were too thin for my application. When you use thin cables, they tend to overheat. So I ended up making my own cables for this power station. The inverter has a metal aluminum housing which is good for cooling. In the back, there's a cooling fan which is activated by above 400 watt output or high temperature. Here is the test setup. Battery is connected to the inverter. Remote switch of the inverter is connected. I'm using a power strip here to connect a small space heater through a kilowatt meter so that we could monitor the wattage and amperage outputs. Here's the initial voltage reading. It's showing about 120. So I'm going to turn the fan on of the space heater without heat, and it is showing about 13 watts here. The inverter display does not show this small power output. At level 1 on the space heater, the power use goes up to 750 watts range. The display on the inverter kind of matches the reading on the kilowatt meter. At level 2 of the space heater, the power usage goes up to 1050 watts and then settles around 975 watts. When I turned the heater to level 3, which is 1500 watts power usage, the inverter overloads and stops working, which is expected because inverter's maximum wattage is rated at 1200. Unfortunately, I did not have a way to use exactly 1200 watts to test the maximum limit. Here is a video clip of that scenario. If I turn it to 1500, the inverter shuts down with an overload. If I switch it back to level 2, inverter works fine. Here is the layout of the build inside the box. I'll make a separate video on the build and post it as part 2.